Section 3.5 is about something called implicit differentiation. And this is going to be something that we can use when we have an equation and we have a corresponding graph. So here's an equation, x squared plus y squared equals 25. The corresponding graph is this circle centered at the origin of radius 5. But that doesn't describe a function. As you can see, I've drawn in this dotted vertical line where x is equal to 3. This graph fails the vertical line test. What that means is that there are two different points on the graph that have an x value of 3. So there are two different y values associated with an input of 3. With a function, each input has to have a unique output, and we don't have that here. But as you can see from these lines that I've drawn in, the notion of a tangent line still makes sense. The tangent line here, I would have to say that that's the tangent line that passes through 3, 4, rather than just the tangent line at 3, because I would want to distinguish it from this tangent line that passes through the point 3, negative 4. But that's still the line that best approximates the curve at that point. Okay, so the notion of tangent line and finding its slope can make sense even if I don't have a function. Now, another way I can see that this isn't a function, I can see it by looking at the graph here. If I were to try to solve for y, I could do that. I could say y squared is 25 minus x squared, but then that would make y plus or minus the square root of 25 minus x squared. So I don't get a unique formula. But this is a kind of nice example because although I don't get a unique formula, I get two very specific options that are functions. If I look at y equals the positive square root of 25 minus x squared, that is a function, and its graph is just the very top half of this circle. I could use this function to find the slope of the tangent line that passes through the point 3, 4. Now it's green. Okay. And if I look at y equals negative the square root of 25 minus x squared, that's a function that just describes the bottom half of the circle. So I could use that to find the slope of the tangent line that passes through the point 3, negative 4. The idea here is basically that both of these functions, the relationship between x and y on the graphs of these functions, is implicitly contained in this original equation. Okay. Any point that makes either of these true also makes this whole thing true. The fact that y must be one of these two functions of x is encoded in this equation. So what we're going to do in this video is we're going to just work out what the slopes of these two lines are, working with these two functions. I'm just going to call this y1 and this y2 so that I'm distinguishing between them. We're going to go ahead and use the tools of calculus that we've learned so far. But what we're going to see is that the process here is very similar to the process here. It feels awfully redundant. And it feels like it would be nice if there was a way to work with just this original equation without having to solve for y first. So, it turns out there is, and that technique is called implicit differentiation. But first of all, we're going to do it explicitly. This is y given explicitly as a function of x. If you have y by itself equals some formula involving x, that is explicitly giving you y as a function of x. So far, that's all the calculus that we've been doing. Here, when I have an equation that gives me a relationship between x and y, for at least almost every point on the curve, if not all, that's going to implicitly define y as a function of x, meaning that there's some function that describes the part of the curve that contains the point that we're concerned about. Okay, so again, let's work through it right now, just working with these explicit formulas. I'd probably rewrite this as 25 minus x squared to the 1/2. And then I could say y1 prime is 1/2 of the input to the negative 1/2. My input was 25 minus x squared times the derivative of 25 minus x squared. So that's going to be 1/2, 25 minus x squared to the negative 1/2, times the derivative of 25 is just 0, and the derivative of negative x squared is just minus 2x. Now, I'm going to simplify this just a little bit. I'm going to cancel those 2's. So I'm going to have negative x, and then I'm just going to rewrite this as the square root of 25 minus x squared on the bottom. Okay. Now, if I wanted to find the slope of this line, I could say I want y1 prime evaluated at 3. Now, over here, just saying that the x value is 3 isn't enough to know which point we're on. But by specifying that it's y1, I'm specifying we're on the top half of the circle, and then the x value of 3 puts me at this point 3, 4. So this would be negative 3 over the square root of 25 minus 3 squared is 9. 25 minus 9 is 16. Square root of 16 is 4. So this is negative 3/4. So I'll just call that m1 and say that's negative 3/4. Now, if I wanted to do this one, don't have much room, but that's okay because it's going to be very, very redundant. y2 I could rewrite as negative 25 minus x squared to the 1/2 power. Then y2 prime is going to be negative 1/2, 25 minus x squared to the negative 1/2, times the derivative of this inside part. Well, the derivative of that inside part is negative 2x. I didn't write out d by dx 25 minus x squared, in part because I was running out of space because I have this ridiculously small board, but in part because this felt so familiar because I did almost exactly the same thing before. All that's different now is there's a negative sign in the front. Okay. So again, as I simplify, I can cancel those 2's. This time the 2 negatives will cancel, and I'll just get x over root 25 minus x squared. y2 prime evaluated at 3 is then going to be 3 over root 25 minus 9, which is just positive 3/4. So this, I'll call it m2, that slope is positive 3/4. This work was so similar, it seems like it would be really nice if there was a way of just working with this equation. And there is. And that way is called implicit differentiation. And here's how it works. We take this original equation, x squared plus y squared equals 25. And we say, okay, encoded in this equation, I know are these two formulas, which are for two functions where I've described y explicitly as a function of x. Without actually solving for y, I'm just going to view y as being a function of x. I know in this particular example, it's one of these two functions of x. If I'm on the top half of the circle, it's the positive root. If I'm on the bottom half, it's the negative root. Okay. But I'm going to say that's some function of x, which makes this a composition. This is a function of x plugged into the squaring function. Okay. So now I've got this equation. We're used to doing the same thing to both sides of an equation. Usually we do an algebra thing. We add 2 to both sides of an equation, or we multiply both sides of an equation by 3. But here, I'm going to do a calculus thing. I'm viewing this as a function. It's x squared plus some function of x squared. And that's equal to this side, viewed as a function. This would be a constant function, where y is always 25. But if two functions are the same, their derivatives must be the same. So I can say the derivative with respect to x of x squared plus y squared is equal to the derivative with respect to x of 25. Not necessary to have these parentheses around the y, but that helps me to remember that I'm viewing this as a function composition. So now I can just take the derivative of each term. So it'll be the derivative of x squared plus the derivative with respect to x of y squared is equal to, and I'm going to go ahead and just say the derivative of a constant is 0. Derivative of x squared is just 2x. Now here, I mentioned that when we got to implicit differentiation, it was going to help you if you had practiced a little bit with the U substitution technique that I showed you when we first learned the chain rule. Because notice here, I'm taking the derivative with respect to x of a function of y. The variables don't match. That again is my sign that this is going to be chain rule. Y is the inside part in a function composition. So I take the derivative of the squaring function, that's going to be 2 times my input, so 2 times y, and I multiply by the derivative of the inside part. I'm just going to call that y prime. You could call it dy by dx. What's going to happen is we have a name for it, but we don't yet have a formula for it. Just like with y. I'm viewing y as some function of x. I happen to know it's one of these two functions. But here, all I have is a name for that function. I don't have a formula for it. So I'm not going to get a formula for its derivative, but I'm going to have a name for its derivative. But this is equal to 0. Now, once I've done this, I want to know what this was. Y prime is representing the slope of the tangent line, so I want to solve for that. So I'm going to subtract that 2x over, so we get 2y, y prime equals negative 2x. To solve for y prime, I would divide both sides by y. Now, of course, if y is 0, that's not legal. So as we solve for y prime, as we do this, we're almost always going to be dividing by some variable quantity. It's understood the formula that we're getting is only valid where it's defined. But here, I would have y prime equals those 2's cancel, negative x over y. And if I apply that here, I'm going to get negative 3 over 4, which we said was the slope of this line. If I apply that here, I'll get negative 3 over negative 4, or positive 3/4, which we said was the slope of this line. So it gives me a way of finding a formula for the slope of the tangent line without having to explicitly solve for y. You will notice there's a big change. We're used to our formula for the derivative itself being just a function of x, so that x is the only variable that shows up. But here, you're going to be allowed to have x's and y's in your formula. That's actually because I don't get the same thing here as I do here, even though they have the same x value. So if I haven't solved so that each x has a unique y in it, I can expect that x and y will both show up in my formula for the slope of the tangent line.